Hi, this is lecture 19 of Applied Statistics, which is a calculus and linear algebra based advanced undergraduate stats course at Bethel University. In lecture 17 and 18, we've been talking about simple linear regression and quadratic regression. And actually in lecture 18, we started using linear algebra, matrix and vector algebra, to describe what's going on. That continues here in lecture 19. Our goal is to talk about the design matrix and normal equations for, first of all, going back to simple linear regression, and second of all, going to our first multiple regression example where we've got two explanatory variables, in other words, two predictor variables. We're trying to predict y when we know x1 and x2. Here is the lecture plan. We're going to first summarize simple linear regression, partially as a review, and partially, mostly even, to view it with this matrix vector algebra approach, partially to tie that to the previous lecture, number 18, and then to set us up next week for more general linear models. When we do lectures 20 and 21, we're going to really focus on the linear algebra in general. We'll even talk about how to think of it minimizing SSE, the sum of the squares of errors, without calculus. In those lectures, we'll talk about a purely linear algebra viewpoint. The key concepts were the normal equations in the design matrix. Then we're going to move on to consider an example with trivariate sample data, values where you've got 3 points for each, 3 coordinates for each point, an x1 value, an x2 value, and a y value. Again, x1 and x2 are going to be explanatory variables. Y is going to be response. We're going to set up the model abstractly, again focusing on the matrix vector algebra. Once again, the key concepts are the normal equations and the design matrix. Third, we'll take a quick look at the initial results that I got from the computer output. Fourth, we'll talk about how I generated the model and the results in Mathematica. And for my students, you should certainly be able to use Mathematica in the ways that I'm going to show you here. Finally, we'll take a quick look at the output for inference, both in Mathematica and a spreadsheet, but I'm not going to really focus on that a ton. Lectures 20 and 21 to come are going to still be abstract. After that point, lectures 22 and 23 especially, I'm going to focus on applications, how to interpret these things, how to really understand the computer output and apply it to real life. All right, so let's start by summarizing simple linear regression. Again, this was the focus in lectures 17 and 18. We've got bivariate data in this case, x's and y's. The x's are our explanatory variables and the y's are our response variables. And we're attempting to model this with a linear function of one variable. In lecture 18, we used a quadratic function. The linear model for the mean of the conditional random variables of capital Y given x, where you're thinking of little x as fixed and capital Y as being an unknown random variable that can take on different values based on some probability distribution. The mean of these things is a deterministic kind of thing. Mu of this random variable is a fixed quantity for any given x, but it's a linear function of x, beta 0 plus beta 1 times x, where beta 0 and beta 1 are unknown population parameters that we would like to estimate. That's one of the main goals, is to estimate those things. But then we want to bring some probability into it. We have a linear model for the individual response random variables, yi's. For any given set of xi's, how do the corresponding yi's vary? Well, they're going to equal their means plus some error term, which I call capital EI. You can see we've got these different notations. For one thing, capital Y sub I is a random variable for a given x equals xi, and that's where the conditional notation makes it a little bit more specific. It equals the mean, mu sub y given xi, plus the error term, where again the error could be positive, it could be negative. You might even say you'd want it to have a mean of 0. And to keep it as simple as possible, we even assume it's normal as well, with some given positive variance. We assume E1 through En, based on x1 through xn being fixed numbers, are independent and identically distributed random variables with this common distribution. Why do we assume this distribution? Because it's the simplest possible model that is often realistic. We can pretty easily derive the parameters and the statistics that we need to be able to calculate. We also have these residuals, these lowercase ei's, E1 through En. Essentially, these are the approximate observed values of the capital EI's. Now, that's not quite right because the capital EI's are related to the population regression line, whereas these little EI's are related to the sample regression line. But essentially, we think of them as being approximations for those things. We seek to minimize something called SSE, the sum of the squares of the errors, errors being synonymous with residuals, as a function of our parameter estimators, which we call B0 and B1. So we think of B0 and B1 as being statistics that estimate beta 0 and beta 1. Actually, in abstract, we saw that we use capital B0 and capital B1, and we think of those as random variables. However, here we're going to focus on thinking of these as being things we're going to calculate based on this minimizing this function. When you look at this equation, we are summing the squares of the residuals, and you want to think of the xi's and yi's as all being fixed. The unknowns here are B0 and B1. We're trying to find what values of B0 and B1 make this as small as possible. Hey, that's a problem for calculus. Take derivatives, set them equal to 0, solve for the critical points. Again, we'll see next week, hopefully, lectures 20 and 21, that you can think of this as with a purely linear algebra approach without thinking about calculus. But for the moment, we're thinking about calculus. So we derive the normal equations, which are the equations to solve for B0 and B1, by taking partial derivatives, setting them equal to 0, and then rearranging to get the normal equations that you would have to solve to be critical points. So here's the partial derivative with respect to B0. Let me get my pen in here to emphasize some things. So the derivative of SSE with respect to B0, think about what you saw on the previous slide. You had this kind of expression squared on the previous slide. I'm taking the derivative of that with respect to B0. Well, first of all, the derivative factors through a summation sign. It's called linearity of differentiation. Then I can just keep the summation sign there. So then the 2 would come down in front. And then keep in mind that you're taking the derivative with respect to B0. You need the chain rule. You need to multiply times the derivative of this expression with respect to B0, which is -1, because you have a negative B0 there. Then you can bring the summation sign through the parentheses. You can cancel the 2. You can rearrange and write it as this equation right here. You can also take the partial derivative with respect to B1. Very kind of similar calculation. Still keep the summation sign here. You'd still bring the 2 down in front. But now you're differentiating with respect to B1. The coefficient of B1 for each of these terms is xi, or negative xi, excuse me. So the derivative of that with respect to B1 is negative xi. That's where you get the extra factor of negative xi there. Once again, the 2 can cancel. You can multiply the xi through the parentheses here. You can bring the summation through. You can rearrange, and you get this equation right there. Keep in mind in these equations, the x's and y's are fixed. It's the B0 and B1 that are unknown. Now you can simplify this further. For example, the sum of the B0s over where I goes from 1 to n is just n times B0, because B0 is constant with respect to I. Excuse me. Likewise with these other terms, the b's can be factored out. You can rearrange, and here's your system of so-called normal equations. I'm going to get a drink of water here. So the n times B0 right there comes from this term right there. You've got B1 times in parentheses the sum of the xi's. That comes from this term right there. And on the other side, you got the sum of the yi's. Down here, you got the B0 factored out of this one to look like this. That comes from that term right there. This one, you factor out the B1, and you're left with the sum of the xi squareds. That comes from this term. And finally, on the right side, this thing right here comes from this one right here. Okay, so it's just a rearranging of this system of equations and simplifying a little bit. That's your system of normal equations in scalar form, 2 linear equations and 2 unknowns. But now we want to think about this in matrix form. And certainly right away we can just write this. Remember what was on the previous slide. You had n times B0 plus B1 times this sum. Thinking about your linear algebra knowledge, taking a 2 by 2 matrix times a 2 by 1 column vector. You do that multiplication when you're multiplying these things, n times B0 plus this sum times that. That would be what goes here, and that has to equal the sum of the yi's. Likewise, when you multiply to find the second entry, you'd multiply this sum right here times B0 plus this sum times B1, which is what you had on the left-hand side of the second equation on the previous slide, and that has to equal the right-hand side, which you see here. So we've got a matrix slash vector equation here. And if we want, we can write this in a more compact form. We can give this matrix a name. I call it A. You can give this column vector a name. I call it C, and I call this column vector B. I wrote it like that. That's not necessarily standard notation, especially with the A and the C, but it's certainly something that can be used. And when you write it like that, if you know some linear algebra, you know that you can solve for b, the b vector, by, well, if a is invertible, at least multiplying both sides of this equation on the left by the inverse matrix of a inverse, and we can certainly do that, at least if a is invertible. It turns out that a will be invertible. It will be if we have more than one data point with different x values, okay? Which, you know, if you only had one x value, you wouldn't be doing this thing to begin with. So that's always a realistic situation. You can write the solution in abstract form. B equals A inverse times C, and if you got some nice technology, or if you don't mind doing this thing by hand, you can actually do the multiplication to find the vector B, which gives you the values of B0 and B1. There is a shortcut formula that allows you to rewrite this. There's a shortcut formula for the inverse of a 2 by 2 matrix with a non-zero determinant. Here is essentially the shortcut formula. What does the shortcut formula look like in general? Let me go ahead and try to write it out with this pen here. In general, when you've got a 2 by 2 matrix like this, A, B, C, D, and you wanted to invert it, you take 1 over the determinant of that matrix, I'll call it capital D, which would be A times D minus B times C, and you multiply it times another 2 by 2 matrix where you switch the A and the D around. You put a D up here and the A down here, and you keep the B and the C in the same spot, but you put minus signs in front of them. So this is the formula that I'm essentially using right here. This is 1 over the determinant of the original matrix on the other side. Try to remember the original matrix on the other side had n in the upper left corner, had the sum of the x squares in the lower right hand corner, and it had the sum of the xi's both in the upper right and lower left corners. This is the determinant of that matrix. And here, I did switch around the n and the sum of the xi squareds, and I did put negative signs in front of the sum of the xi's. By the way, both of these matrices are symmetric in this case, and that's going to be the case in general in this situation. So it didn't really matter that these are the same thing. The B and the C are the same thing in this case. That gets multiplied by the C matrix, C vector, that's right here. This can be rewritten in this way that you see here. By actually doing this multiplication here, I can write this. And this expression down here can be written as n times what I called SS sub xx. My students should know what that is. And for my students, it's going to be an exercise for them to check the very last equality here, that this all simplifies to this. Okay, and this is related to other formulas for B0, this thing right here, and B1, this thing right there. Okay, so my students are going to be checking that very last equality here. All right, I talked about the design matrix at the beginning of this lecture too, but what is that? I did talk about that in lecture 18. Let X be the design matrix, also known as the model specification matrix. What is it? Well, in the quadratic model from lecture 18, it was a n by 3 matrix where it had 1s on the first column. I had x1, x2 through xn on the second column, and I had x1 squared, x2 squared through xn squared in the third column. Something similar here with simple linear regression. I've got 1s in the first column and just x1 through xn in the second column. It's an n by 2 matrix this time. It's a little simpler. The multiple regression model that we'll do here in a few minutes will get a little bit more complicated again. Its transpose, which we talked about in lecture 18, is xt. This t is not a number, it's not a power, it's just the transpose where we switch the rows and the columns. So the first column of x becomes the first row of x transpose, all 1s. The second column of x becomes the second row of x transpose. By the way, as we go through this, both in this lecture and lectures to come, it's really important, you should know if you've taken linear algebra, to keep track of the dimensions of your matrix. So X, you can see, is an n by 2 matrix, n rows and 2 columns. Its transpose is a 2 by n matrix, 2 rows and n columns. That's important in terms of what happens when you multiply these matrices, and even knowing that you can multiply them. And we can take X transpose times X transpose being a 2 by n matrix, X being an n by 2 matrix. The inner n's match, so we can do this multiplication. The outer numbers, the 2's, mean the result has to be a 2 by 2 matrix. And you should confirm in your mind that this multiplication does give us, hey, this is the original A matrix from the normal equations. that I had a few slides ago. Think about it. To figure out the upper left entry of the product, I'd multiply 1 times 1 plus 1 times 1 plus dot 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 plus 1 times 1. That is going to be an n right there. For the upper right entry, I'd multiply 1 times x1 plus 1 times x2 plus etc. through 1 times xn. That's going to be this summation right there. For the lower left entry, I'd multiply x1 times 1 plus x2 times 1, etc. through xn times 1. That will be this summation. And finally, for the lower right entry, I'd multiply x1 times x1 to give me x1 squared, x2 times x2 to give me x2 squared, add that, etc. Keep adding until you get to xn times xn. The last term you add is xn squared. It gives me this summation here. That is the thing I called capital A on a previous slide. So, to summarize, we can also let, well, this is one more thing. We can let y be the column matrix, column vector of the corresponding y coordinates of the data, this vector right here. I can multiply x transpose times y, this 2 by n matrix times this n by 1 matrix. The n's match, we can do this multiplication, and we're going to get a 2 by 1 matrix, a column vector, that is the right-hand sides of the equation that I had before, capital A times B equals C. That was the equation that I had on that slide before. And so we can write the normal equations in this way. This is the same as capital A right there, x transpose times x. This is B, and this is the same as C. And I can solve for B as A inverse times C. This is just another way to write A inverse. Well, A is x transpose times x, and A inverse is then x transpose times x inverse. And that is another way to write the solution of the normal equations. Note, this cannot be simplified really any further in terms of x. You cannot take this inverse operation and bring it through the parentheses here. You might think you could. You might think you could write it as x inverse times x transpose inverse. But no, x and x transpose are not going to be square matrices. They don't have inverses. The product is a square matrix. It has an inverse, at least if it's determinant is non-zero. But those matrices individually do not have inverses. Okay, so it cannot be simplified further in terms of the design matrix X. All right, now we're on to our multiple regression examples. So once again, what we just did was we went back to simple linear regression, and we saw that we can view it in matrix form. That was the point. Now we're going to look at a multiple regression example with some data, although right away here I'm going to go to the theory right away. It's only at the end that we're going to come back to the data and we're going to look at the results. But at least here initially look to see that we have a trivariate data. We're going to think of this ultimately as sample data from some population. I'm picking the x1 and x2 in a sort of a deterministic way, and then the y's are random in a sense. So the y is really ultimately your random variable in the model. And notice the x1 goes from 1 to 3, and for each such x, x2 goes from 1 to 4 in whole number increments. That was just to keep things simple. And we got the random variability in the y's. Okay? It's hard to just look at a table like this and understand what's going on. It'd be nice to make a graph, and we will see a graph here soon. And it'd be nice to try to model this with some sort of regression model. But what is our model? Now we'll go back to the theory again. Once again, we have a linear model for the mean, and also a linear model for the individual response where we add on an error term. The mean is a deterministic function, linear function of x1 and x2, where beta 0, beta 1, and beta 2 are the unknown fixed parameters that we would like to estimate. But again, mu is the mean of this conditional random variable. I'm thinking of x1 and x2 as being fixed. These are fixed, and then the value of y is unknown. It's random. Okay, y given x1 and x2, it's a random variable, but its mean is a fixed quantity for when x1 and x2 are fixed, and I'm assuming it's a simple expression in terms of x1 and x2. Why? Because it's nice and simple, and we hope it's accurate. But the yi's themselves as random variables are the mean plus some error term. Now notice I added a little extra in here. I added some i's. I've got n data points, okay? When I'm thinking about this in terms of the original data, I can think of those as being data points with two coordinates if I like, x11 comma x21. The 1 here corresponds to the fact that it's the first coordinate, And the second one would correspond to the fact that it's the first data point. The 2 here corresponds to the second coordinate, and the corresponding 1 would correspond to it being the first data point, x1, 1, comma, x2, 1. But then I would be set 2. I'd go to the second data point. I'd have x1, 2, comma, x2, 2. The 2 that comes in the second spot in each case emphasizes the second data point. Through, etc., n data points, I'd have x1n and x2n as being the last one. That's why I've added on the extra i's in these spots here. Once again, E1 through En are all independent and identically distributed random variables with a similar kind of distribution, normal with a mean of 0 and some unknown positive variance sigma squared. We'd like to estimate sigma squared as well, and perhaps its standard deviation, which is called the regression standard error. Once again, the residuals, the little ei's, are approximate observed values of the capital EI's, but with respect to a sample regression line instead of the population one, we seek to minimize, once again, SSE as a function of our parameters. So now SSE is a function of 3 variables. In this expression, B0, B1, B2 are the unknowns that you'd like to solve for by minimizing this thing with calculus. Though again, next week, hopefully, we'll minimize it with linear algebra. And so we do the calculus now. We take the partial derivatives on this slide, and you can just glance over this, maybe pause the video and double check things. This is correct. In the first line, we have the extra factor of -1 here because we're differentiating with respect to B0. And the derivative of that with respect to B0 is -1. You use properties of algebra and rearrange to get this equation. Second one, we're differentiating with respect to B1. Notice the coefficient of B1 is -x1i, so that's why we get an extra factor of -x1i there. Rearrange, etc. You get this equation. Partial with respect to B2. The chain rule, I need to differentiate that with respect to B2. It gives me an extra -x2i that you see there. Once again, simplify, rearrange, you get this equation. Okay. If you rearrange these equations, we have the corresponding normal equations. There we are. Isn't that pretty? So once again, it's a system of linear equations, this time 3 equations and 3 unknowns. Once again, you have a term in the upper left corner that is an n times B0, and all the other terms' coefficients are various kinds of summations. Be thinking right away here about the matrix that we're going to get, the matrix form of the normal equations. It's going to be a symmetric matrix. The number here matches the number there. The number here matches the number down here. The number here matches the number down here. It's a symmetric matrix. The summation squared terms are on the main diagonal right there and there. And then you've got these summations on the right-hand sides. Okay, so I'm about to show you the matrix form of this. There we go. But I'm going to go to the design matrix right away, actually. I could have added an extra slide in here where we just looked at the normal equations without thinking about the design matrix. So now the design matrix is going to be n by 3, like it was for the quadratic regression from lecture 18. First column, all 1s. Second column are the first coordinates of all the data. Third column are the third coordinates, or the second coordinates of all the data. Now this notation, unfortunately, is, well, it's unfortunate in that it's a little inconsistent with how we typically denote entries of matrices. Well, for one thing, these numbers here all start with a subscript of 1, and they're not in the first column. That's one thing to be aware of. A second thing to be aware of is they're also just not in the first row. The second numbers keep going up by 1. Usually it's standard notation with matrices that when you go down a matrix, it's the first subscript that keeps increasing. And when you go to the right on the matrix, it's the second subscript that increases. So this is inconsistent with that standard notation with matrices. However, it is the best way to do it in this context because, once again, these are all the data, the first coordinates of all the data points. So I want to keep those 1s in the first spots as they are. Okay? And this column here, those 2s in the first spots, emphasize that these are the second coordinates of all the data points. So just bear in mind it's not consistent with the usual notation for entries of matrices. Its transpose would be this. This would be then a 3 by n matrix. The first column of the original matrix becomes the first row of the new matrix. The second column becomes the second row. And the third column becomes the third row. All right. With this particular one, it is a little bit more consistent, and now that we go down these columns, these numbers do increase in the first spot. But we still don't, they're still not in the first row. The ones are in the first row, so there's still some inconsistency there. And we can write the normal equations in this way. We can once again do x transpose times x times b, where b is the unknown vector that we'd like to solve for. If you multiply x transpose times x, you get this 3 by 3 square matrix, and just double check in your mind, this is a 3 by n matrix times an n by 3 matrix. The inner n's means you can do the multiplication, the outer 3's means the answer is a 3 by 3 matrix. Yes, double check. You essentially take the dot product of the first row with the first column, you're going to get n. Take the dot product of the first row with the second column, you're going to get this summation. The dot product of the first row with the third column, you're going to get this summation. I'm saying dot products assuming you've heard of dot products before. Dot product of the second row with the second column, you will get this, let's see, this summation. Okay, dot product of the second row with the first column will give you this one. Dot product of the second row with the second column will give you this summation with the squares in there. Those things are the same, x11 squared plus x12 squared, etc. Dot product of the second row with the third column, now the first subscript of 1's gets matched with the second first subscript of 2's. So we have summation x1i times x2i. Once again, this is a symmetric matrix. This number matches this one, this number matches this one, this matches this. It's a symmetric matrix. Its transpose equals itself, actually. There's the unknown vector. There's x transpose times y. I didn't actually simplify it, but that's what would be on the right side. The simplified form of those was on a previous slide with the partial derivatives, with the scalar form of the normal equations. Didn't have room to put it on here. The goal, once again, is to solve for this B matrix, the B vector, excuse me. You'd want to multiply both sides on the left by the inverse of x transpose times x. All right. I'm not actually writing that out, because now we're going to look at the data, we're going to look at the results. So here again is the data. Maybe you want to pause the video and take a screenshot of that or something. Now we're going to go ahead and look at the results that I did get from the computer. Turns out that the sample regression equation that is obtained by minimizing SSE and solving for the critical points, solving for B0, B1, and B2, that does minimize it, is this one right here. B0 is 4.4638. B1 is negative 0.0176. And B2 is positive 0.3812. Got three different notations there on the left. You would use different notation here depending on the application. Maybe just use a plain simple y hat if we're just emphasizing that we're trying to predict y when we know x. Use this kind of notation if we're trying to emphasize that this is going to be an estimator for this conditional random variable of y given x1, x2. And use this notation if we're trying to emphasize to use the regression line to estimate the mean, to estimate the population regression line, the linear model for mu. You can use any one of those notations. I generated the sample data in a special way in Mathematica that I do want to share with you, especially with my students. It was based on a particular fixed deterministic model for the mean. I picked this one. Mu sub y given x1, x2 is 4 minus 0.25 x1 plus 0.75 x2. In other words, beta 0 is 4, beta 1 is negative 0.25, and beta 2 is positive 0.75. So based on the sample data, sample size 12, and is 12 here, we got these individual estimators for these population parameters. For a small sample size of 12, I guess I would say it's not too bad. One that's furthest off in a sense is maybe this one. And there is also in the model, you need that the errors are normal with a mean of 0 and some variance that I picked to be 2 squared, which also means the standard deviation would be 2. And I did ultimately generate this graph that you see right here. And so this is a three-dimensional graph. You can see the how this is labeled is this x1 labels this axis here going to the right. That's the x1 axis. because that label is, in a sense, parallel to that axis. Don't be confused by the fact that the x2 is down there. x2 is parallel to this line, which means it's parallel to this axis. This axis is the x2 axis. The red plane that you see here is the population regression line. That is exactly deterministic. It's the assumption that I made. That's the thing that we're trying to approximate with the sample regression. Did I say line? I meant plane. And that's the graph that's in blue. The data are in black. What are these green lines? These green lines are essentially, well, they have signed length equal to the residuals. Positive residual when the point is above the blue graph, negative residuals when it's below. And these lines are to the blue graph here, not to the red graph. Okay, so that's a visual of what's going on with your trivariate data. You want to think about it graphically, three-dimensionally. All right, let's now go on to the Mathematica and then on the spreadsheet to finish off the lecture here. So I do want to show my students and anybody else who's interested how I generated the data. We are going to look at a spreadsheet too here, if you're more interested in looking at the spreadsheet output. So in Mathematica, here I defined my population model as a function of the two variables x1 and x2, and I went ahead and entered that. And using table and random variate in this way, I'm able to generate random data based on this model. And every time you enter this, you're going to get different random linear data. The x1 and x2 are deterministic, and they do go from 1 to 3 and 1 to 4, respectively. And then the y is mu, plus this thing is essentially EI, capital EI. Normal distribution with a mean of 0 and a standard deviation of 2. Mathematica requires you to plug in the standard deviation there rather than the variance. That's the normal distribution that the EIs all have. This random variate essentially samples from that distribution according to some method that the Mathematica is programmed to do, giving us different data every time that we enter it. For this video, I used a particular run of this, and I'm calling this fixed linear data, and then I just copied and pasted essentially there. To get it in a form where I can analyze it easier, I had to do something special called flatnet. Don't worry about what that does. It just makes the data easier to handle. How do you actually get the regression line, a regression plane equation, I should say? Fit can do it. Just a plain old fit can give us the regression equation. So here is our regression equation. 4.46 minus 0.0176x1 plus 0.3812x2, which I typed into this function of x1 and x2, and I'm calling it y hat. Okay, thinking of this as being my sample regression line, and I can enter that. This code makes the three-dimensional plot. Kind of a lot of code there to make that. There might be a more efficient way to do it, but well, that was lots of fun for me to do that. And one thing nice is in Mathematica is you can actually move this around here a bit to see it. And you can see that those green lines do go to the blue plane instead of the red plane. They are the residuals with respect to the sample regression plane. Okay, let's think about it in terms of the design matrix and normal equations as well, which my students should be able to do. So here I plugged in the design matrix. And by the way, for my students, well, and anybody else who's interested, to plug in such a matrix, I can use this writing assistant, which you can get at from the palettes menu, this writing assistant right there. And you can enter a matrix initially as 2 by 2. And if you want to enter another column, you can do a control comma that adds a column. And if you want to enter more rows, you can do a control return that enters more rows. So this was how I made the matrix. That's a nice way to do it if you use this button in the palette here. Anyway, so that's the design matrix. Notice the first column is all ones. The second column are the x1 values. The third column are the x2 values. And I can look at what does x transpose times x look like. This is going to be my capital A matrix that's going to be 3 by 3. I get this, and these things do equal the summations that we saw in the PowerPoints. And this 12 here is actually n. 24 is the sum of the xi's. If you add up these numbers, you should get 24. Yeah, we get 4 plus 8 plus 12 is 24. 30 should be the sum of these numbers. 4 plus 3 plus 2 plus 1 is 10. You got 3 groups of those 10, so you have 30 for the summation. 56 should be the sum of the xi squareds. You square these things, you get a bunch of 1s. You square these things, you get a bunch of 4s. These, you get a bunch of 9s. We're going to get 4 plus, what would it be, 16 is 20, plus 36 is 56. Okay, 60, that should be what? The sum of the products of these things, I think. And the 90 should be the sum of the squares of these things. So you should take the time to double check that. Here's the y matrix column vector. These are the third coordinates from the data that I generated. X transpose times y will be a 3 by 1 column vector. This is the sum of the yi's. I think this was the sum of the x1i's times yi's. This is the sum of the x2i's times yi's. We can solve for b0, b1, and b2 using solve in this way. Don't forget your double equal signs there. This solves for b0, b1, and b2. 4.46, negative 0.0176, and positive 0.3812, just like we saw before. We also could solve it with an inverse matrix. This essentially inverts the capital A matrix and multiplies it times, that's the C vector, which is X transpose times Y. The dot is the matrix multiplication here, by the way. You see a dot there as well. You don't use star in Mathematica for matrix multiplication. You use a dot, period. And we get the same answers, 4.46, negative 0.0176, positive 0.3812. We can do all this with linear model fit and do more. So here we're getting a little bit into inference. Now I'm not going to explain all these results right now. That's going to be for a future lecture, probably lecture 22 more. But linear model fit, when you enter it, doesn't seem to do much besides give you the equation, but it is storing a lot of other information in this variable that I'm calling LM for linear model. And by the way, I could have called it something else. I could have called it, F or something like that. It doesn't matter what you call it, but now you can access that information through various commands here, like parameter table, parameter p-values, etc. This would correspond to doing inference. T-statistics and p-values for hypothesis tests, for example. And you can also do confidence intervals. Your confidence interval, this is for the intercept to estimate beta 0. This is to estimate beta 1. This is to estimate beta 2. Notice the p-values and the intervals contain 0. The p-values are kind of big, and the intervals contain 0. We don't really have strong evidence for these data that it is a significant regression in this context. Okay? Hopefully for more real-life data, you would get p-values that are really small, and you get confidence intervals that are either all positive numbers or all negative numbers, depending on the situation. You can look at the intervals themselves. You can change the confidence level. The default level is 95%. You can look at the y hat values for the different data points and the residuals. We can do confidence intervals and prediction intervals as functions of x1 and x2, or we can plug in numbers as well. Actually, this is kind of interesting. We can plot this prediction interval upper and lower limits as functions of x1 and x2. We get two surfaces that are not actually planes, and that should make sense if you followed the other lectures. We can look at individual prediction bands, confidence intervals for the original data, and prediction intervals for the original data points. To me, these don't have a ton of meaning because you're doing it for the original data points. This is more useful when you're thinking about other values of x1 and x2. I know that went by quick. We will get into that in more detail later, but let's get on to the spreadsheet to finish things off. So here I have the x1 values in this column, the x2 values in this column, and the corresponding y values. Let's just show you that the XL Miner analysis tool pack can analyze this, though we're not going to look at the details a ton here. So once again, we do linear regression. I always, as a first thing, click the labels box as a default, because I like to include the labels. That's a good idea. Click on the Y range, well, highlight the Y range, including the label Y in cell D3, and then click on Y range. And then for the X range, click on both. Make sure you highlight both the X1 and X2 column, then click on the input X range. Let's just get the output. I'll put that in cell F3 for the upper left corner. Click on output range, and now click OK. And we're going to see multiple regression output. For example, we see down here, let's make this a little smaller. Well, it's too small. You see the coefficients. These are B0, B1, and B2, same numbers as before. You see the t-stats and p-values that we saw before. You see the confidence intervals that all contain 0 still that we saw before. These p-values are not too small. You see an ANOVA table. I didn't talk about that before with Mathematica, though you can get that to come out with Mathematica. And something different here when you compare this to simple linear regression. We saw with simple linear regression that the significance f here, a p-value there, matched the p-value for the slope with simple linear regression. This number, this p-value, however, does not match either of these two p-values. So with multiple regression, something different is going on here. And ultimately our goal, again, probably starting in about lecture 22, is to understand more deeply how to interpret these numbers. Thanks for watching.